So Paula mentioned their investments for the Snorri program, which of course is dear to our hearts. I would like to now turn to a special Snorri, Madeline Stapleton, who will be moderating a presentation on the recent volcanic activity in Iceland. Madeline received one of our convention awards this year, and she is also a member of the Icelandic-Canadian Club of Toronto. She's a Falkinn editor for that organization. She's also a graduate of Queen's University with a degree in geology as well as GIS training. And she's a Snorri from 2022, which makes me feel quite elderly with a Snorri of 2006. So you can tell it has been 25 years that this program has been running. So can I now turn to Madeline to start the presentation?
Thank you. So up next, we're going to have the presentation on the recent volcanic activity in Iceland. So we're lucky to have with us today Professor Þórðarson. He's a professor in volcanology and petrology at the University of Iceland, and he'll be giving us a presentation on the current activity. Following the presentation, Erik Schoonover, a fellow Snorri 22 participant and a fourth-year PhD student at Penn State University, currently studying granites and related igneous rocks, will begin a 20-minute discussion with Professor Þórðarson regarding the ongoing activity. So for the duration of the presentation, could you please remain on mute as well as turn your cameras off? And if anybody has any questions, if you could put them in the chat during the discussion period, we'll try our best to answer as many as we can. So now on to you, Professor Þórðarson.
Yeah, good afternoon, everyone, and it's a pleasure to be with you, and thank you for this invite. Before I start my presentation, I think it's interesting to hear of this development in terms of collaboration between Iceland and Canada. And while I'll be talking about active volcanism, it's worth pointing out that most of the valuable or critical metals that we use in our industries and to maintain our lifestyles are actually associated with volcanic rocks and thus with volcanism. So it might be a basis for an extensive collaboration in this field of volcanology. Maybe think about things like applied volcanology, which then might help us to develop better exploration models for those critical metals. And should point out, Canada is, of course, one of the largest producers of raw materials in the world. So I think there's a potential there for fruitful collaboration. Anyway, what I want to try to do is to give you a summary of the current volcanic activity on the Reykjanes Peninsula. And not too scientific, hopefully. Let's hope that this is, I'll manage to give this in a language that so everyone can actually both enjoy and understand. Now, one question: do you see the display set?
Yep,
full slide?
We can see the screen.
Yeah, but do you see a full slide or do you see a split screen?
Split screen.
Yeah.
Is that a full slide now?
Yep, full slide.
Yeah. Okay, that's it. Anyway, so like I said, we're going to talk a little bit about the volcanic activity in the Reykjanes Peninsula. And of course, I'm a member of a group, or one of the leaders of a group in volcanology and natural hazards in Iceland, that we sort of undertake research related to practical sides of volcanology as well as academic sides of volcanology, and the same thing with natural hazards. And the list of the other members in here are listed here below. And we've been working on this for quite some time, and we got some large number of collaborators through two European funded projects on natural volcanic hazards on oceanic islands in the Atlantic, and also some research, both academic and practical research on volcanic material in Iceland and how that can be utilized to further our understanding or our lifetime. Anyway, this is just a sort of list of some of those people that are involved. But what is Iceland? Iceland is, as all you know, in the middle of the North Atlantic. It sits on the juncture between what we call the mid-ocean Atlantic Ridge or mid-ocean ridge, which is basically a plate boundary where one plate is going directly to the west, and the other plate, the Eurasian plate, is going to the east, as you will see a little bit later. And but beneath Iceland, there's also a mantle plume that is superimposed on this sort of plate boundary. And the interaction between these two things have actually created Iceland, and are the reason why it's above sea level. The rest of the plate boundary is actually submerged and beneath sea level, but Iceland rises 1,000 meters plus on average above sea level, and sort of between 3,000 and 4,000 meters above the surrounding seafloor. So it's a huge mountain plateau, which the volume and the areas is shown here. So this includes the Icelandic shelf, of course, and this is all produced by volcanic activity in Iceland. And just to sort of give you some indication of the size of this, the gigafactory in Tesla gigafactory in Texas, covers 930,000 square meters. So you would actually need about 2 billion gigateslas factories to cover Iceland, and this is for similar numbers for the volume. So it is, it's very big area. It's a very big volcanic area, one of the biggest on Earth today. As we probably all know, this plate boundary, the Reykjanes Ridge, is part of the plate boundary, and it sort of approaches Iceland from the south. And as it comes to Iceland, it sways, onto the Reykjanes Peninsula, and then it joins with what we call the Western Volcanic Zone, which extends basically from Hengil to Langjökull. And this plate boundary, the plates on either side is spreading 1 centimeter per year in either direction. And that spreading is semi-continuous, and it builds up strain on the plate boundary, which then is relaxed in episodic events, which quite often result in what we call rifting and volcanic activity. And this is what we're basically seeing on the Reykjanes Peninsula. Here you can see an image of Iceland. It's from Sigurjón Jónsson, which is at Kast in Saudi Arabia. And it is showing the part of Iceland that is spreading directly east, which is here in the red and yellowish colors, versus the part that is actually going west, which is in bluish colors. And the boundary between these two things is roughly the plate boundary as it is thought to actually be in Iceland at present. And so there's the Reykjanes Peninsula, and we can see that the plate boundary across the Reykjanes Peninsula is not sort of a north-south orientated like most of the rifting segment in Iceland and on the Reykjanes Ridge, but it's actually the west to east. So it is the movement there, as we will see a little bit later, is that it's kind of a lateral movement. Part of the Reykjanes Peninsula is going west, and part of it is going east. But this boundary is not quite parallel to the spreading direction, so there's a little bit of an extension which actually allows for the volcanism that we see on the Reykjanes Peninsula. Up here is a photograph by Otto Sigurðsson, and it shows just where the Reykjanes Ridge basically is coming on shore on the Reykjanes Peninsula, which is the area of the Reykjanes Peninsula which is called Reykjanes because of the geothermal activity. And of course, we have a geothermal power plant out there as well these days. And I just threw this in. It's a satellite image of recent satellite image of Reykjanes Peninsula taken on 8th of February this year, and shows the structures of the Reykjanes Peninsula quite well. The Keflavik Airport, the greater Reykjavik area, Grindavik and Þorlákshöfn over here, Vogar, And then, of course, the town of what we used to know as Keflavik and Njarðvík, but it's called Reykjanes today. And this grayish cloud here, and there's the one that goes offshore here, is actually the plume that is coming off the volcanic eruption that actually started in the morning on the 8th of February. And just to sort of briefly mention the history of the Reykjanes Peninsula and the volcanic history of it, the areas where, like the Keflavik Airport and the greater Reykjavik area, these are older rocks that are actually outside of the active volcanic areas and are fairly stable. And we don't expect anything to happen on these areas, or neither in terms of earthquake-related movements or volcanic activity. So Reykjavik area is not going to experience an eruption within the population limits, or the same thing goes for the Keflavik Airport. Maybe I'll just change this roughly here. Point eruption. Keflavik Airport, which is stands much higher, so it's not going to be really directly affected by any lava flows or tectonic movements, but it could be impacted by pollution, gas pollution, and tephra fall or ash fall, as you probably know this in terms of terminology. But you see, most of the rocks in the volcanic rocks that form the Reykjanes Peninsula, and those of you who've been to Iceland know that when you drive across it, you drive across these, and past these lava flow fields, they're all fairly young. So the oldest exposed rocks in the Reykjanes Peninsula are a few 100,000 years old, but most of the sort of the old volcanic rocks that are produced by recent activity are less than 15,000 years old, as shown by these numbers here. And you see these green areas here, these are actually what we call lava shields. And they are very large lava flow fields that are produced by single eruptions. Some of these eruptions took place about 40,000 years ago. Others are significantly younger, about 7,000 years ago. But these eruptions played a key role in actually tying what is Romskvalsnes, where the Keflavik Airport is, to the rest of the Iceland mainland. Before that, this was probably an island. And so the volcanic activity have made a key contribution to actually building up this part of Iceland and putting it above sea level. And now this is the most populated region in Iceland. But it's all relatively young, and there's no surprise that people are actually exposed to volcanic activity in this area. And like I said earlier, the plate boundary comes up across, from the ocean, rises up out of the sea here on the Reykjanes, and it goes across the Reykjanes Peninsula, and then it continues here up the western volcanic zone. This red arrow here shows the spreading direction, or the plate movement away from this plate boundary. And you can see that they're sort of a sub-parallel, but there is a slight difference in angle, and that difference in the orientation is the reason why there is an extension taking place on the Reykjanes Peninsula, which actually makes it possible for magma to rise to the surface. That basically the tectonic movement, the movement of the plates, the push in this direction and that direction, opens up fractures and cracks and faults that allow the magma to come towards the surface in an eruption. And it's actually quite important that even though there's a constant movement out here roughly to the west and a constant movement out here roughly to the east across this plate boundary which is in here, it does not necessarily mean that this is material in here is moving constantly. What it is, it's been stretched over a period of time, and you built up the stress in it, And when the stress has built up enough that actually the stress is greater than the strength of the rock, which is in here, then the rock snap. And they usually do so in specific zones across this peninsula, which is actually where we have the volcanic activity shown here in with these red lines. And so we have actually an extension in this area, opening of fractures and magma coming to the surface. And because of this is episodic, what happens is that we have periods which are quite long, between 600 and 800, sorry, 1,000 years long, where we are basically stretching the rocks in this volcanic area here on the Reykjanes Peninsula, and we don't have any volcanic activity. All we're doing is basically just like a elastic band. You start initially stretching it, but as you stretch it more and more, it gets harder and harder to stretch it, and eventually the elastic band will break, and same thing happens to the crust. And when that happens, we open up pathways for the magma to the surface, and we have a period of volcanic activity, which we refer to as eruption periods. And these eruption periods, they can last for 300 to 400 years. And of course, there's not a constant volcanic activity, but the volcanism is also episodic in this period. So we will have a period of several eruptions over a few years or even a few decades, and then things will go quiet for some time, and then it will pick up again. And as it does currently, is what we're experience is actually one of those periods where the crust snapped, and it did so here around Þorvaldur and also around Stundhnjúkur with Grindavík. And so we are actually in one of these volcanically unrest and spreading unrest areas, which we usually refer to as fires. So it's a common thing to talk about in Icelandic as fires, like the Fagradalsfjall fires or Fagradalsfjallselda. But it's important to know that and realize that this activity that we see here in the Reykjanes Peninsula is periodic, and we are now starting a new period, and we will have this, most likely have these events like we're experiencing now repeated fairly frequently over the next 200 to 400 years. This is actually quite interestingly contrasted by the volcanic activity on the Reykjanes Ridge, just southwest of the Reykjanes Peninsula. And this is just a bathymetric map showing the volcanic structures of the Reykjanes Ridge as it approaches Iceland. And the numbers here are all the eruptions that we know of on this part of the Reykjanes Ridge in historic time. And you can sort of see that the activity here is sort of roughly an eruption or two per century, and which is very different from the pattern that we see on the Reykjanes Peninsula. And the reason for that is because here we have the orientation of the plate boundary is very different than across the Reykjanes Peninsula, and it's a much more of a spreading situation where you would have more frequent opening events and thus more frequent eruptions. Also, some of these eruptions have formed islands, and maybe the best known one is the island that was formed in 1783 out here close to Eldeyabodi. And this island was formed in February 1783, so prior to the Laki eruption that caused the Haze famine. And as it was being built up out of the sea, some Danish ship captains were sailing past here. They noticed this island. They informed the king about the island, and he got very excited. So he sent out a ship with a flag because he wanted to claim this new island. And when they got there, the island was gone. So the ocean had basically eroded it down. So it was a very short-lived island. Wonder if I can get rid of that. Yes, I can. Okay. Now, in the last 3 years, we've had 7 eruptions on the Reykjanes Peninsula, and here we have the list of the first 3 ones, which are in Fagradalsfjall, and you can see the map of the lava flow fields that were produced during these eruptions, and these numbers are just giving the sizes and volumes of these things. But maybe the key element here is to notice that these lower numbers or smaller numbers here at the bottom of each, which range from 4 to about 6.5 cubic meters per second, that's basically the discharge or the productivity of these eruptions, which is very low. If productivity of these eruptions drops below 3 cubic meters per second, so roughly, at least according to theory, then the eruption will stop. So these are eruptions that barely made it to the surface, and where the magma barely made it to the surface, and they sort of and barely maintain these eruptions going. And so these are low intensity eruptions, and they're also very small volume, and that's sort of kind of the message that we want to put forward here. Why don't I get? Okay. Each of these eruptions actually has some precursors, and this is what is monitored in Iceland, mainly by the Icelandic Met Office. And we can see basically two things. We can see that the ground is inflating, it's rising, and it's moving, and not only up, but also laterally. And that's because the magma that is underneath is making trying to find a way or path through the crust, and it actually causes displacement of the surface. And that's one key, but the other signal that we see as an indication of something is going to happen in terms of volcanic activity is the earthquakes. And these events at Fagradalsfjall, they were preceded by fairly intense earthquake swarms that lasted for well, the first one lasted for 3 weeks, and then they got shorter as the events went on down to a week. But they also featured quite strong earthquakes, some of with magnitude over 5, and which were felt in the greater Reykjavik area and elsewhere in Iceland. Before I go talk a little bit more, I'll show you some images from these events. I want to show you a time lapse that is from the 2021 Geldingadalur eruption, and it's taken over 2.5 days. And it's when the lava was filling in Náttagi, a small valley south of the eruptive fissure. But the reason why I want to show you this is because it's a very nice example of a typical emplacement mode for lavas. And maybe the biggest surprise in that is that most of the lava is not incandescent, as it's been emplaced into the valley. And this is quite an important thing, because lavas have a tendency to form crust that actually insulates the liquid interior and keeps the liquid interior hot, maintains the heat within the lava, and that allows the lava to actually flow fairly easily across the landscape and also build itself up and produce quite a long lava flow fields. But let's just go through this, and hopefully I can get this going. Interesting. Yeah, I'm gonna do something else here. It may have something happened in the copying, but it doesn't really matter if, okay, here we go. It's just the same thing. No, that was not what I wanted to do. Jesus. Okay, we're just gonna have to do it this way. Sorry about that. I'll run it again. But take a notice that most of the surface is cold. There's only occasionally you see incandescent lava on the surface, but you're pumping lava into the core, in the liquid core. You can see the lava surface keeps rising. And lava flows can do this, and they can increase their own thickness by a factor of 5 to 10 through this process. Let me just quickly run that again. So you can see it spread out as a thin sheet initially, crust forms on it very quickly, insulates the interior, maintains the liquid interior, but then that kind of like keeps extending the lava, but also increases thickness vertically by this inflation. And this mechanism kind of ensures that the interior of the lava stays hot, and the lava has a capacity to flow quite a distance. And let me just go back to this. So now there it goes. Now this is just an image from the 2021 eruption. It lasted for 6 months. That's the first event. Very low magma discharge on the order of 4 to 8 cubic meters per second, but it created actually quite some spectacular scenery and spectacular show. And here is actually a photograph taken from the greater Reykjavik area, and here's the Hallgrímskirkja. And you can see the fountaining from the eruption actually quite high. They actually approached the height of Hallgrímskirkja. Then we had the second eruption, which lasted for 3 weeks. It was in August 2022. These are just images from the vent area. And then we had the Litli eruption in 2023, which lasted for 4 weeks. And the main sort of hazard from that eruption was actually it ignited the low growth around in the region of the eruption and caused quite an extensive vegetation burn that created a substantial pollution. And this is the shift over from Fagradalsfjall over to Sundhnúkur, just north of Grindavík. And that's the fourth eruption that happened in right before Christmas on 2023 on about 3.5 kilometer long fissure, and you can see Grindavík here in the background. And lasted only for 2 days and had quite a high magma discharge. The maximum magma discharge in this event was about 400 cubic meters per second. But because the volume available for eruption was very small, about 10 or 14 million cubic meters, the eruption was out of juice very quickly, and it was over within less than 2 days. Similar, the Hagafell eruption in January 2024 started also with fairly high magma discharge, a few hundred cubic meters per second, but was over within 1.5 days for the same reason as the previous one. But this one did damage. It actually, the fissure opened up through some of the protective walls that we've been building around both Grindavík and also around Svartsengi, the power plant, and the Blue Lagoon. And so part of it was erupting on the town side of these protective walls and produced lava that went into town. But unfortunately, also a fissure opened up here just outside of town and produced small lava flow that actually went into town and burned 3 houses. But most of the lava, though, which is very important, is that it was produced by the part of the fissure that is outside of the protective wall, and that the lava produced by that part of the fissure was actually kept at bay from the town by the protective wall, so it actually worked really well. And the sixth eruption is the 8th of February, as we mentioned before. We saw the images from those, and then that eruption started at the same location as the 18th of December eruption. But but also sent lava flows to the west. And that lava that went to the west actually marched down the slope, which was reasonably steep, at least for the lava flow, more than 4 degrees. And that lava kind of marched over the road to Grindavik and closed it off. Also, more importantly, it actually reached the hot water pipes from Svartsengi and severed those pipes. So the towns of on the Reykjanes Peninsula were without water for almost a week after that. 16th of March, which is the one that is currently ongoing, and is the longest eruption of these along the Sundhnúkur volcanic lineament. Started very similar to the others, but for some reason it actually managed to keep on going. It actually managed to tap deeper resources of magma to maintain its activity. And this is just a little sort of a comparison. It's important to realize that even though when we stand out in the field and look at these eruptions and the lavas they produce, they are actually fairly small. Here they are compared to the 2014-15 Hollersheim lava flow field. And you can see that in general, these are about 1/10 of what was produced in 2014-15 on Dyngjusandur. So these are all very small, low intensity eruptions. And just to show the state of the activity as of 15th of April, this is the yellow is the new lava flow. And activity started on a fissure that extended from roughly about here and about 3 kilometers to the north up to here, but quickly was concentrated on a single vent, which is now continues to be active. And that one is producing lava flows, and you can see that most of the lava is basically piling up very close to the vent. It's not managing to go very far because the magma discharge is very low at the moment, or just above 3 cubic meters per second. Here you can see the 14th of January lava flow that also caused some damage within Grindavik. And so the general pattern that we've been seeing in these eruptions is that you see the land at Svartsengi rise to a critical level when you reach the sort of the critical stage where the magma volume is putting so much strain on the surrounding rock that they actually fail. Magma then drains out of the volume where it was accumulating, and the land subsides, and you have an eruption. Magma moves towards the surface in an eruption, and then you start accumulating magma into that storage zone again. And when it reaches a critical level again, you have to repeat the event, and we've done this several times. And the diagram here to the right is just showing the volume that accumulated in the storage zone, the shallow storage zone, before eruption. And we can see that in one case, it's just about 19 million cubic meters, but in most cases, it's just barely above 10. And the one that is ongoing right now, there's inflation ongoing, and that volume is now approaching just above 10 million cubic meters, which people sort of generally think is critical volume. We can expect something to start to happen when we reach that stage. Now, what does it look in the subsurface? And this is a view that we have been presenting based on the data that we have analyzed, which is also slightly different from what the Met Office does, but we've also have some additional information that they have not been able to use. So it is clear that sort of at depth between 8 and 12 kilometers, there is actually a fairly large magma storage underneath the Reykjanes Peninsula, the western part of the Reykjanes Peninsula, and it's centered on Fagradalsfjall. This storage is about 10 kilometers wide, and it's about 10 kilometers long, might be longer than that. And it is 3 to 4 kilometers thick. And most of this magma accumulated at this location in the time period between 2002 and 2020. So it was not there in 2002. And so it started to accumulate sometime in that time period. And we're talking about the volume here is about 300 to 400 cubic kilometers. So it's a very large magma storage, sort of deeper magma storage here. The one that we've been hearing most about in the news in terms of causing inflation in Svartsengi is this smaller magma storage at 4 to 5 kilometers depth. And this magma that is flowing from this deeper one up here has been accumulating in this smaller one, the shallower magma storage. And when that shallower magma storage has exceeded about 10 million cubic meters of magma, its roof has failed, and that has led to an eruption. So this is orders of magnitude smaller than this one down here. And so this is sort of explains the pattern that I showed you earlier, but also what's happening in the current one is that on the 16th of March, this magma chamber had reached the critical level. It ruptured the roof, and magma flowed out of it to the surface in an eruption. And but it did not close the pathway as it did in previous events at the end of the drainage. But the magma that's coming from below actually managed to get up through and continue and maintain this eruption going, and that's what it's doing right now. And for a period of time, and that's what is causing the inflation now, is that part of the magma that is coming from here goes all the way up, part of it goes into this shallow magma storage, and it's filling that up again. Just a few things about volcanic hazards. One might think that you could expect eruptions anywhere on the Reykjanes Peninsula, but that is not the case. If we look at geological data, then we see that the areas, and this is what we call eruption susceptibility. It's basically using statistics, using geological data to predict where the most likely places for eruptions are on the Reykjanes Peninsula. And the brighter colored the brighter the colors are, the higher is the potential for an eruption at those within those areas. So these high bright colored areas, that's where the most likely places for the eruptions in the near future. The paler the color is, the less likely it is for those areas to have eruptions. And most of these eruptions produce lava flows, but they do produce gas pollution, and also can produce some asphalt, like we had in Surtsey, submarine eruption of Surtsey. And these events can, of course, have an impact on population centers in the neighborhood, so people living there, also on infrastructure. We've seen that already. Even though it's a small event, they can have significant impact on infrastructure. And of course, they can have impact on business and also on tourism. And the best way to deal with these things is to understand these events very well, have some plans for how to respond to them, and also how to prevent their impacts. And sort of to highlight the areas where lava flows are maybe threatening, most threatening this. We know Grindavík, and we know what's happened there. It's been severely impacted, but similar thing could happen to Reykjanes. They could also have impact on Vogar. And also the outskirts, lava flows could reach outskirts of the greater Reykjavík area, or in Hafnarfjörður, they could even extend through inhabited areas and all the way to the shore. And maybe the one of the more worrisome impacts of lava flows on the Reykjanes Peninsula is that if you have lava flows from a single eruption reaching the shores on the north side of the peninsula and the south side of the peninsula, that would mean that you would take out all the main traffic arteries in the area, both Suðurstrandarvegur and the Reykjanesbraut, and that would mean our international airport would be isolated and disconnected from the rest of the country. And that could have severe economic impacts. I'm not going to dwell on this, but yes, we know that location of eruption site is important, and the size and intensity of magnitude of these events also important. But it's also very important that people are actually prepared to take on these events. And so part of our preparation for the future is that I've been involved in what's called the infrastructure group, and we are the group that promoted building of the protective walls around Svartsengi and around Grindavík, and they've proven to be very successful, as I mentioned earlier. For example, in the January eruption, they kept this lava flow away from the town. If the wall was not there, then this lava would have gone into town and probably destroyed far more houses than it did. And just to illustrate how effective these walls can be, these are lava simulations. This is not reality. This is modeling. But we have modeled lava eruptions, for example, from vents here just north of Grindavík, and what would happen if there were no protective walls. So basically, Grindavík would be inundated in lava. But if we have the walls, then we could keep the lava from the town and let's save the town, at least from lava flows. And we can look at this also in terms of multiple eruptions in the area and its impact on both Grindavík and Svartsengi. And it's clear that the protective walls are a worthwhile investment. So with that, thank you.
Thank you very much. Just put any questions you have in the chat, and Erik, on to you.
Thank you, Professor. That was amazing. Well covered, and I think it was definitely approachable for everyone. Yeah, I have some questions, but I think we should start with the ones in the chat because there's a lot of questions on, I guess, safety. So Stefan asked a question about noticing people around the lava flows and if that was safe. I guess the question would be also who were in those videos looking at lava flows. And then there's also the question of, will this advance to a point of this being viewable by other people who are not in the press or science communities?
In terms of safety, I mean, it's important to realize that, well, I guess most of you probably used to Fahrenheit rather than centigrade, but the lavas are very hot. And if you have, like you see here, incandescent lava like this, that's right there at about 800 degrees C. They can be up to 1100 degrees centigrade. So we're talking temperatures which are in excess of 2000 degrees Fahrenheit. If you get too close, you will burn. And you might not be life-threatening, but you will definitely get burns, and that can change. The state of that can change over a distance of a few inches. So you might be safe if you stand 3 or 4 feet away from it, but if you go 1 foot closer, it will burn you. So that's one of the dangers of being not up close to lava flows. The other thing is that, as you saw maybe in the video, is that as the lava is moving across the landscape, you see these sort of breakouts from the margins of the lava, and sometimes those breakouts can move very fast. We have examples in Iceland where such breakouts have actually moved at speeds of 60 kilometers an hour. And you never know when that's going to happen. Or whether it's going to happen, but since it can happen, then and if it does happen, then you're not running away from it. And so you going into look and part of this whole exercise is for people to actually be able to go and watch these eruptions from a safe distance. So you don't want to be right in front of advancing lava. You don't want to be in the low-lying areas. You want to be higher up. That's the way they say. Another aspect of dangers in terms of these eruptions is the gases. And SO2 can be sometimes heavier than the atmosphere, so it will sink. The same thing goes for CO2. And if you're exposed to either of those gases, those are toxic and dangerous. So if you breathe those in, that could be fatal. Also, sulfur dioxide converts into sulfuric acid or sulfuric aerosols, which is even more toxic than the SO2. So again, if you're watching these kind of eruptions, you want to be upwind of the active events and the activity, basically. Does that answer people's questions?
I think that was very comprehensive for sure. So there are also some questions about the magma storage, and this is actually where a lot of my research is for granitic magmas. But for we have a question about the length of time it takes for the storage to cool, and then another question about the threat of eruption for those magma storages as well.
Well, if we look at these, and this is just to note that this is not necessarily drawn to exactly to scale. For example, this should probably be significantly smaller than it's shown. The shallow magma storage, if you put magma in there and it doesn't drain, that will probably take some decades for it to cool down and stiffen up in such a way that magma is never going anywhere. This deeper storage, which is much, much bigger. So here we're talking about 1/100th of a cubic meter. Here we're talking about 300 to 400 cubic kilometers, sorry, and 1/100th of a cubic kilometer. So this is going to stay molten, at least partly molten, for centuries, if not thousands of years. So it can be active, and it could feed eruptions in this region for the next few hundred years. So yes, this, and especially if magma is still flowing in here, and if you're increasing the pressure in this deeper magma storage, it might maintain eruptions near Svartsengi or near Sundhnúkur, but it also could produce some new eruptions, for example, in Krýsuvík up here, or even further out in Eldvörp, and even extend. There's no reason why it can't extend laterally and become bigger, and then it could actually produce events in Reykjanes. So yes, this magma storage is probably going to be the main source for the activity in Reykjanes Peninsula in the near future.
Thank you. Yeah, so I guess further on the storage question, a lot of these drawings have these red circles that imply that there's melt there, but I think a lot of the picture is sometimes that it's a pool of just melted magma right there. How much melt is actually there percentage-wise versus like a crystalline rock?
That's something we don't know exactly, but I suspect the fraction of melt in the deeper magma storage is probably over 30%, at least. It's also interacting with the surrounding. So this area here, which is referred to as lower crust, is actually a part of the crust which is in ductile form and probably already contains some melt, even though it might be in small fractions. And there is interaction between whatever came in here and what was there before. But this volume here is actually accumulated in less than 20 years. And well, that's the indication of the data anyway. And if that is correct, then I suspect that actually a large part of it is actually liquid. There has to be enough liquid there for it to move easily. And so it would be more than what is expected from close compaction of solid material. So it would have to be more than 35%.
Is there any concerns for this magma evolving or concentrating volatiles to be more explosive than its current like effusive state?
I think we should be. If we are not concerned about that, we should be, because one of the things about this magma body here is it is what we refer to as fertile magma. So it is actually a fresh batch of new magma which could be related to the material that is coming up in the mantle plume. So and if that's the case, then it actually is fairly volatile rich. So it would contain fairly high or relatively high concentrations of water, CO2, and SO2. CO2 would be a great concern here, because that can start to exhale from the magma at these steps fairly easily. And that could start seeping up, and there's some of the ESOR scientists, they wrote a paper in, when was that, in 21? Rather than, maybe it was published in 22, where they were arguing that there was the inflation observed both at Svartsengi and Krýsuvík in 2020 was actually due to movement and flow of CO2 in the crust rather than magma. I know that not everyone agrees with that, but that is a suggestion there, and if that can happen, then those events can even build up and produce something even bigger.
So do you think that there's any play here with glacial melting and causing more of like the reduction in pressure to increase volcanic activity?
I am not a big believer in glacial melting having that impact on the deeper regimes of the crust or the upper mantle. And the reason I say that, people have made this observation, and it's true that we have lost a fair bit of ice from Iceland in recent decades, and there is a general rise. The central part of Iceland is rising, and some people have interpreted that as because of the melting of the glaciers. But I just remind people that more mass is removed from Iceland by wind erosion, and mostly from the highlands, than is moved by glacial melting. So if you want to make that kind of argument, then you would have to take into account the material, the solid material moved by wind and river erosion, and which actually that mass is far greater than the ice mass. So maybe there's a contribution from both. I don't know. It's possible.
Interesting, very. So we have some questions about kind of the like engineering solutions here, and I guess a starting question would be like, how do you predict where to build the barricades?
How do we, sorry?
How do you like predict? Are you using these models? Are you using past eruptions? How would you decide where the most beneficial spot is to build the barricades?
We're using all of the above, all of the available data to us, and accurate topographic models are very important. So you look at the lay of the land, and the lay of the land in connection to where most likely places are you're going to have eruptions. That's why it is also we can do these kind of maps in much greater detail. We can zoom in on areas, but that's why it's very important to know where the most likely site of eruptions are, because then you can place eruptions in here, and we can run models that will show where the lava will flow. And we have a fairly good model that will show fairly accurately the path the lava will take. And we also have these models here, which actually predict reasonably well not only the path they take, but also the extent of the lavas. So we can, using all the geological information that we have, all the volcanic history, very detailed digital elevation models, and then we can basically sort of find the highs or the elevation divides in the country, in the landscape, and that's where you place the protective walls on the highs, and then so they can actually divert flows away from important structures and into lows that are on either side. So it's a combination of number of things. So that's why in the infrastructure group, we have volcanologists, we have engineers, we have model experts and all these things. And that's how we managed to do it.
And it seems like it's worked really well with all the data that you guys have. So another question about an engineering solution is, do you think it's possible to like engineer a way to act before an eruption? The question is if you could like drain it off or divert it earlier, or do you just have to wait until it erupts to react after these predictable models?
Well, I've been a very strong agitator for preventive measures, and there's a lot of things we can do. Kind of a modeling work and work that will sort of help us to assess where are the most likely places where it might erupt, what kind of eruptions are we going to get, and what kind of lava flows are these eruptions going to produce, how fast will it go, how big will it be, et cetera, et cetera. We can do all of these things up front. We can start doing that now. We can have that ready. And if we do this for vulnerable areas, when we know that if there's a lava producing eruption in the near future, then we can have things in place. We don't have to start to build the protective walls right away, but we can have all the designs, the preparation, the materials that we need that can all be in place. So it will take much shorter time to build protective walls if need be, or do any other kind of mitigation measures that people might deem necessary to protect the important infrastructures. But it takes effort to do this upfront, and it really needs to do. We need to do this upfront, and that's what we have not been doing. Everything that has been done, and everything has been done to date in Iceland, is response. It is not preventive. It's not. We have not been prepared, and people have been fairly careless, and that includes authorities.
Yeah, I guess that was going to be my follow-up question is like, currently with all there's the academic viewpoint and these engineering solutions, what has been the support that your institution or groups have received from the government or other independent companies, things like that? Well,
in the infrastructure group, this is basically by the infrastructure group was set up by the government or the authorities, and it was the natural hazards insurance company that actually instigated it, and now it is the civil defense that sort of oversees that activity. The infrastructure group includes private companies, so engineering firms. So it is a mixture of government, university people, which are usually from the University of Iceland, which is a state university. And so there's a mixture of group there. The leader of the group is actually from one of the engineering firms. The government has put up a lot of money to pay for the activities. It's basically funded directly by the government, both the activity in the group and also all the activity that we have suggested that to be done in the field. And it's not cheap, but it is, if you compare the cost of building those protective walls to the infrastructure, the cost of building the infrastructure that they're protecting, the cost of the walls is fraction of a percent of the total cost of the whole thing. But this is, I mean, in terms of monitoring, that is all with the Met Office, and that's all government run.
Yeah, I know the funding structures for academic research differs across the world right now. So it's interesting to hear your viewpoints there.
Well, we don't get any money to do academic research.
Yeah.
That's one of the big gaps in this, I would say, because we're missing out on opportunities of learning.
Mm-hmm.
I mean, it's a very different thing to do research on an active eruption to learn how it actually functions and understand better how the lava flow and improve our flow models and our understanding of the whole thing, versus be sort of in a responsive mode where you're actually just focusing on protecting something or saving something. So we are losing out at the moment on academic research, big time, because there's no funding structure available for academic research to actually get money to go out and do those things. And we can't, as an academic, I can't just go out there and do it, because it costs money to get there, it costs money to have people working, and you have to take them from other projects which are already funded and are paying their salaries, etc. So, yeah, we need to think about solution in that realm, really, how we're gonna maximize our learning from individual event, because each event is really, you can think of it as an experiment. You know, you do physics, you set up experiments, and you have it all very well structured, and you measure all the different things. And in this case, in the case of an eruption, you want to be able to do the same thing, but you have to use the opportunity when it comes, and you have to be ready to put out all your tools for measurements. And that such a deployment does cost money. It doesn't cost a lot of money, but it costs money.
Yeah, it seems difficult, and it's such a good opportunity to study these like fundamental processes. But we've got a little bit of time here, and I think there's a really good question here, probably for maybe everyone else here, is that just kind of, so I know I read about these things in kind of academic journals and things like that, and that can sometimes be a barrier to the general population. Do you have any good recommendations for people to learn more about this? Maybe not in the academic journal setting, but just for the general population?
Yeah, there's a lot of good coverage. I think Reykjavik Grapevine has been covering these things fairly well, and so is We Could Poster it. And they have some quite good articles and interviews that cover these events. There's a lot on YouTube, and it's really worth going on YouTube, and certainly not all of those people are volcanologists or heavily involved in those things. They're just interested in disseminating the information to the general public, and some of those sites are actually quite good. So I suggest that you guys just search YouTube. As you can search YouTube for many other things, you can also search them for volcanic eruptions in Iceland.
Thank you, Professor. This was great, and I've certainly learned a lot. I hope everyone else did as well. But I'll take a little leave here and let Madeline take it on here.
Awesome. Thank you very much, both of you, for all the information you guys have provided and shared. This was a wonderful presentation, so thank you very much. And I'm going to pass it back to Ashley.
Well, thank you all for listening, and thank you for having me.
Oh, thank you, Professor Þorvaldur. Yeah, that was wonderful. And we have all been watching the developments in Grindavik over the past year. And certainly having the science background of what is happening and understanding it a bit more is very interesting, especially that video with people getting so close to the volcanic activity and the magma flow. That was very interesting, and a little bit daunting how powerful the Earth is. And Iceland has so many interesting geographical features that of course have driven this tourist boom. But also when you go back there, you do feel like it's a special part of the world with so much going on under the surface. But thank you so much. And also thank you to Gwen and Erik. Thank you for joining us. Just wonderful to see these brilliant young Snorris who are giving back to the INLNA by participating in these presentations. And yes, thank you for that, because I think this is the kind of thing people are interested in, and to learn more and have that insight is great. So I think now we're